All right, I'm going to pick up with the Chapter 5 notes here. We're on problem 10, where it says a person can have one of four blood types, that's A, B, AB, or O. If a person is randomly selected, is the probability that they have blood type A equal to 1/4? Why not? Well, there's four blood types, right? So is it 1/4? And the answer is no, because blood types are not equally likely, meaning that they're not equal in size. So, in other words, the number of people who have blood type A in the world is not the exact same number as the number of people who have blood type B, and that's not the exact same number as as the people who have blood type AB, etc. So blood type O is sometimes called the universal blood type, because I think it's almost half the world has blood type O, and blood type AB is the rarest of all the blood types, because I think it's only like 3.8% have blood type AB. So they're not equal in size. Okay, so to say it's 1/4 would be not true. Problem 11. Let the sample space for an experiment be the set of counting numbers 1 through 10, and let F be an event in the sample space. What is the probability of F? So the way that we define probability is we want the number of things in set A divided by the number of things in the sample space. So the probability of F would be, well, there's 4 things in F. There's 10 things in the sample space. 4 over 10 reduces to 2/5. Okay? So 2/5 would be the probability of selecting one of these numbers in F. Problem 12. Exclude leap years from the following calculations and assume each birthday is equally likely. Okay, part A. Determine the probability that a randomly selected person has a birthday on the first day of the month. So there's 12 months total, right? There's 365 days in a year. 12 of those months are going to be the first day of the month, right? So 12 divided by 365 is approximately 0.033, or there'd be roughly about a 3.3% chance that you meet somebody and they're born on the first day of the month. Okay. Part B, determine the probability that a randomly selected person has a birthday on the 31st day of the month. So the probability of 31st day. So 7 months have 31 days. All the others have either 30 days or 28 days. So 365 days in a year. So there's 7 divided by 365, or that'd be roughly 0.019 is the probability. So, it's more likely that somebody would be born on the first day of the month rather than the 31st day of the month, because there's more first days than 31st days. Part C, determine the probability that a randomly selected person was born in December. So there's 12 months in a year. December is 1 out of the 12 months. And some people write 1 out of 12, which is not true. So the way to look at this is there's 365 days in a year, and December has 31 days in it. Okay? And you want the number of things in the event divided by the number of things in the sample space. It's all about the days, right? 31 divided by 365 is roughly 0.085, or there's an 8.5% chance that somebody is, born in December. Why is it not 1 over 12? Well, that would be true if the months were equal in size, and they're not equal in size, right? So some months have 28 days, some months have 30 days, some months have 29. Some months have 31 days. Okay, so the sizes are different. Okay, so if they were all the same size, then it would be 1 over 12. But you don't want to look at it in terms of that, though. Part D says, determine the probability that a randomly selected person has a birthday on December 21st. Okay, so there's 365 days in a year. December 21st is only one day out of those 365 days. So 1 divided by 365 would be 0.003. Okay, there'd be a 0.3% chance at randomly guessing someone's birthday is December 21st. Okay. Part E, if you just met somebody and she asked you to guess her birthday, are you likely to be correct? Well, so many people would say, no, you're not. Well, why is that, though? Well, the probability is very small, right? So we see here in the case of December 21st how it is 0.003. Okay, that'd be true for any one of the days in the year. So, no, the probability is very small. Okay, so it's likely not to happen. Problem 13 says, in the game of roulette, a wheel consists of 38 slots numbered 0, 0, 0, 1, 2, 3, 4, etc., all the way up to 36. To play the game, a metal ball is spun around the wheel and is allowed to fall into one of the numbered slots. Part A, determine the sample space. So they kind of already told us what the outcomes were. So it's 0, 0, 0, 1, 2, 3, right, all the way up to 36. Now the only extra thing that you'd want to do there is that you'd want to include set bracket notation. Okay? Now everyone would do that, but that has to happen because of how we define a sample space, right? The sample space is a set of all the possible outcomes. Okay? Part B says determine the probability that a metal ball falls into slot marked 8. Okay? Well, so there's 38 slots total. When I look at this, only one of those is slot 8. Right? So 1 divided by 38 would be the answer. Part C, determine the probability that the metal ball lands into falls into an odd slot. So there's 38 slots total. 0 is an even number. You'd assume 0, 0 is also an even number. So if I'm only looking at 1 through 36, and you know how many of those are odd, well, half of them are going to be even, half of them are going to be odd. So there's 18 even, there's 18 odd numbers. There's 20 even numbers, including 0 and 0, 0, on the roulette wheel. 18 divided by 38 reduces to 9 over 19, so 9 over 19 would be the answer there. Okay, problem 14 says the spinner shown below is spun twice in succession to create a 2-digit number. Assume that it is equally probable that the pointer will land on any one of the 4 numbered spaces. If the pointer happens to land on a borderline, just disregard that spin and spin it again. Okay, that way you get a definitive number to work with. Part A, determine the sample space. So if I spin the spinner once and it lands on a 1, and then I spin it again and it lands on a 1, then the number 11 would be created. Otherwise, if I spin it for the first time and it lands on a 1, and I spin it for the second time and it lands on a 2, the number 12 would be created. Okay, spin it for the first time and it lands on a 1, spin it for the second time and it lands on a 3, the number 13 would be created. If you spin it for the first time and it lands on a 1, and spin it for the second time and it lands on a 4, then the number 14 would be created, okay, etc. So what if I spin it for the first time and it lands on a 2, and I spin it again and it lands on a 1, and the number 21 would be created, okay? And so I've got these, looks like 16 numbers that would be part of the sample space. Now, sometimes I see students write this as ordered pairs, like the dice problem. So if you remember the dice problem there, I was using ordered pairs, and the reason why is because I was distinguishing what number I saw on the red die versus what number I saw on the green die. Okay, and that was in the directions there. Not the case here. So in this dice rolling problem, we're creating an actual number, right? You wouldn't write your number 11 like like this, would you? So no. or any number for that matter, right? So the fact is that this is a totally different problem in that you're creating an actual number, whereas the dice rolling problem, that was just to distinguish what outcome I saw on the first die versus what outcome I saw on the second die. Part B, what is the probability that the resulting number is 23? Okay, well, out of all 16 of these numbers listed, only one of them is the number 23. And by the way, I'm writing the event next to the probability sign. So I commented that in the last video, how you always include the event next to the probability sign. So don't just write P equals or anything like that, okay? So, and sometimes we got to write out in words, what we're computing. Part C, what is the probability that the resulting number is greater than or equal to 23? Okay, so I'd look at how many of these 16 numbers I have listed are greater than or equal to 23. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 are greater than or equal to 23. So 10 over 16, that's going to reduce to 5/8. And so 5/8 would be my answer. Okay. Problem 15 says if a family has 4 children, find the probability that there are 2 boys and 2 girls. Assume that boys and girls are equally likely. So you're not on any medication or whatever that's going to give you an advantage over getting a boy versus a girl or vice versa. Okay. So each gender has an equal shot at being identified. I'm going to let B be boy and G be girl. That way I don't have to write out boy and girl each time. So the sample space would be the first thing that I have to know. So what are all the ways that this family can have 4 children? Okay, well, one way is if all 4 are boys. Okay. Another option is if you have 1 girl and 3 boys. Now the 1 girl can come either first, second, third, or fourth. So I'd have 4 outcomes to list there. Another option is if you have 2 boys and 2 girls. Okay, so let's see, the 2 boys could come first, 2 girls second, or the 2 girls could be born first, 2 boys second. Girls could be born in the middle, or boys could be born in the middle. They could alternate genders, so go boy, girl, or girl, boy, boy. Okay, and I think that's all for having 2 boys and 2 girls. Now, I want to list, I want to finish listing all the ways I can have 4 children. So I got no girls, 1 girl, 2 girls. What if I have 3 girls? Okay, that means that I've got 1 boy, and the 1 boy can be born first, second, third, or fourth. So I'd have 4 elements there to list. And then, or the last outcome is if I have all 4 girls. Okay? Now, so if I count the elements there should be 16 total that I've got listed. And I need to find the probability of having 2 boys and 2 girls. Well, out of the 16 elements that I've got listed, there are 1, 2, 3, 4, 5, 6 out of the 16. So 6 out of 16 reduces to 3/8, or there'd be a 3/8 probability that I get 2 boys and 2 girls. Now, by the way, one way to look at this is, okay, there's 4 children, there's 2 boys, 2 girls, that's half and half, right? So the answer should be 1/2. No, it's not 1/2, right? That's because of all the ways that you can have 2 boys and 2 girls. So the point of this is to say that the sample space is absolutely critical to getting the right answer. Okay, so because I mean, if anyone said 1/2 is the answer, that they'd be wrong, right? But the thing that they're not looking at is all the ways that they can have, you know, all four of these children. Okay. When we stop the video right here, and I'll pick up with problem 16 in the next video.